Right, so let's start today's class. So yeah, we say that for a normal distribution is the proper term for probability bell curve, okay? And for this, we usually have what we call standard deviation of 1, like for normal or for a standard normal distribution. Remember yesterday I showed you that is a different let me open this. Okay, remember yesterday saying that normal distribution, or we say a data set is normally distributed with the mean sigma, okay, and standard deviation, sorry, with the mean mu and standard deviation what? Sigma, okay, or variance sigma squared if you want to use variance, or if you want to use standard deviation, you will go with mean mu and standard deviation what? Sigma. And that's why we say that um, normal distribution is basically defined by mean and standard deviation as well. Then we have what we call standard normal distribution. Okay, so standard normal distribution, it's normally distributed with mean 0 and that is standard deviation what? 1. Okay, with mean 0 and standard deviation as what? As 1. This is for that is a standard normal distribution, meaning given that is a data set which follows a normal distribution with mean mu and standard deviation sigma, we can now standardize. Okay, we can now standardize that is that normal distribution to what? To make it as norm that is a standard normal distribution. Okay, that is by making its mean to be 0 and its standard deviation to be what? To be 1 through a process known as standardization. Okay, and for standardization we usually use what we call z-test. We have a z-score that is a z-score formula. Okay, yes, we have a z-score formula. I can't really remember that is the formula, but I guess it's mu divided by that is minus mu divide by standard deviation, but we can always confirm. Okay, yes, we can always confirm. So standardization function, standardization function, that is for normal distribution standardization formula or function. Yes, I just want the formula. Yes, it is this one. The xi's, it is the xi's minus the mu, which is the mean, divide by what? Standard deviation. You can see that it is z, that is the z formula, that is its x values minus mean divided by what? By standard deviation. Okay, so that's how we can standardize a normal distribution using that function. Maybe during our practical sessions we'll do that is some practicals to illustrate that. Okay, yes, so we were saying that in a normal distribution the mean is 0 and standard deviation is 1. This is a standard normal distribution. Okay, and then its that is its skewness is 0 and a kurtosis of what? Of 3. Okay, meaning like for a standard normal distribution, let me just try to see if I can plot a standard normal distribution. Okay, I can see we have that is the mean. Okay, that is the mean. It is that is the mean. We've said the mean is 0 for standard deviation. Mean is 0. Okay, then we have standard deviation. Standard deviation is what? Standard deviation is 1. Okay, we've said that also skewness skewness is what? Skewness is 0. Okay, skewness is 0. And then we have kurtosis. kurtosis kurtosis is what? Kurtosis is equals to 3. Okay, all right, give me just 1 minute. I can see an urgent call, and then I will be back. Okay, just 1 minute, please. Just 1 minute. Okay, sorry for that. I'm back. All right. So basically, we've said that for a standard that is normal distribution, okay, the mean, you can see all these for all these three, all these 4 factors, okay, can be used, even used as what? Can be used as that is properties of what? Properties of a standard that is a normal distribution. Okay. Yes, like we know, mean for standard normal distribution is 0. uh, for 1, okay, that is for standard deviation is 1, skewness is 0, and kurtosis is what? Is 3. Okay, so basically meaning if we get another value for maybe skewness, anything maybe between -1 to 1, that is for for the value of skewness, we'll know that if we get 1, we know this data is skewed to the what? To the right, like it is positively skewed. Okay, most of the of our data lies to the what? To the, that is to the right of the, that is of the normal curve. Okay, so basically in that situation we'll say that of course the distribution might be normal, but it is not a standard normal distribution. Okay, only these properties apply for what? For a standard normal distribution, meaning we can have other normal distributions which maybe they are that is a like they have different or they are portraying that is different properties. Like you might find a, a kurtosis which is less than 3. Okay, meaning maybe somehow our data is what? Is skewed, even if it is trying to that is to assume a normal distribution, but it is skewed to one side. Okay, all right, good. Don't worry, we shall discuss all this about skewness. It's now our next that is a topic. All right, good. So normal distribution are symmetrical, but this is the point which I was trying to explain. That is, normal distribution is are symmetrical, but not all symmetrical distributions are normal. So in reality, most of pricing distributions are not perfectly normal distributions. Okay, like you might find sometime maybe the data is what? Is skewed. So we can say we have a perfect normal distribution. For perfect normal distribution, it's only the standard normal distribution. Then we have some applications of normal distribution, and we are saying that remember yesterday I gave you this example about marks scored on the test. We have heights of different persons. We have also the size of objects produced by a machine. Also maybe the blood pressure. Okay, if you are monitoring the blood pressure, there of course we'll have majority that is with a normal blood pressure. Some will have low blood pressure and others will have high blood pressure. Okay, right. Let's go now to skewness and kurtosis. Now we have to define what is skewness, okay, and what is kurtosis. Let me start with skewness. So basically skewness shows us that is like how our data is what? Is distributed. Okay, and basically we usually have positive skewness and negative skewness. Okay, so basically skewness is the major measure of what? Asymmetry. It's the major measure of asymmetry of distribution. So skewness in statistics is measure of asymmetry or the deviation of what? Of a given random variable distribution. Okay, from what? From symmetric distribution like normal distribution. Like for example, we know this is, that is our first plot. It's our standard normal distribution. You might also sometimes get maybe your data is what? Is looks like a normal distributed distribution, but more that is this is the curve maybe we are getting. Okay, this is illustration number 2, and then we have illustration number 3. Okay, then you might have this also kind of distribution. Okay, right, this is illustration number 3. So basically this tries to show us that is the skewness of our data, or where is our data mostly concentrated. Okay, that's why we are talking about a positive skewness and what negative that is skewness. Okay, all right, let's continue. So in a normal distribution, we know that mean, mode, and median, mode, and mean are equal. That is for a standard normal distribution. Okay. But now when it comes to skewed data, then these won't apply, because mean won't be equal to mode, and mode would be equal to what? To mean. Okay. So for skewness in statistics is divided into two categories: positive skewness and negative skewness. Okay. Yes, let's start with the positive skewness. So the data now, I want us now from what? From whatever we are going to read here. Okay. I want you now to tell me which kind of skewness is positive and which is what? Negative. From what? From our definition. Okay. All right. So the extreme data values are higher in a positive skew distribution, which increases the mean value of the what? Of the that is of the data. Okay. To put it all together, a positive skewness distribution has the tail long on the what? On the right side. Okay. Meaning we'll have outliers at what? At the that is at the right side. Okay. Whenever like whenever we have in now the long tail, it's where now we will have most of what? Of our outliers. If the values within the tails are high, definitely they will push the mean. Remember we say that during measures of central tendency, mean is affected by what? By outliers. So in case we have or that is high values, or large values to that is mostly within the long tail. Okay, or the tail, uh, then our data or our mean will tend to be shifted to what? To that side. Okay. Yes. So all this means that mean is greater than median, and it's also greater than mode in a positive skewness. Okay. Then let's go back to illustration. Can someone tell me that is which illustration between 1, 2, and 3? Which illustration represents positive skewness from our description? Yes, Collins.
I think it's illustration number two.
Number 2. Why?
Yes,
Why?
because when you look at the drawing, then let me say it's getting fatter to the right.
But that's not the case, because remember we said something here.
Hmm.
For a positive skewness distribution as the tail, okay, or as the tail on the what? On the right side. Yes, Collins.
When you say the tail, do you mean
This is
the
the tail.
the values are higher or the values are lower?
So this is the tail. Okay. So let's assume this is x-axis. Okay. We
Hmm.
have values from 0 to what? Let's say even to 100. Okay.
Uh-huh.
Then we can say maybe most of scores are in here, are between here. Okay. So in this case, okay, we will know that maybe let's assume this it's cut what? These are cut scores. Okay. We have majority having scores between 10, let's say, and what? Say 10 and 60. Okay. But we have some people, few people who have what? And 80, 60, 90. Okay. What will
Mm-hmm.
happen to the mean?
The mean will shift because of the few people.
Then it will shift to which side? Is it to this side or is it to this side?
I think it will shift towards the 100 mark.
Yes. Why? Because we will have, because remember when we are talking about the long tail to the right, then it means that like we have also more people in here. Okay. And let's assume maybe most of the people here are averagely scoring. Okay. Let's assume we have let's just get an example of five people. Like we have five, that is 30. We have 50. We have 55. We have 40. And we have 35. If we do mean of this, can someone maybe do average? Let me check my. Yeah, someone maybe can quickly do.
I think it's 42.
The average is 42. Okay. All right. I want us now to add some outliers to the positive side. Okay, like add 80 and add 90. We'll only just get only two. Just get two. Just do now the average of all these. You can see
54.28.
now 54. So you can see our what? Our our mean is increasing. Okay. So meaning now our data will be somehow skewed. Okay, to this side. Okay, that's why we are saying that whenever we have a long tail, okay, on the right, then we have a positive skewness, meaning our data is skewed to the what? To the that is to the right. Then whenever we have that is a long tail to the left, okay, meaning our data is skewed to the left. Why? Because we have some outliers to the what? To the left. Okay. So this tail, that is long tail, really affects what? It really affects our data. Why? Because if we head the tails to the both sides, then this could what? This could have this could have maybe moderate or could have maybe removed those outliers. Why? Because we have some extreme value, small values and also extreme that is high values. Okay, and that will take like a normal distribution, but for skewness then this will be what? This will be a positive skewness, that is a negative skewness. This will be a positive skewness. Okay. All right, just 1 minute. Okay, sorry for that. That was just checking on something. It's work related, which I was requested. But yeah, I'm good. We can continue. So let's maybe check for the negative skewness before we can do what? Before we can maybe conclude on skewness. So for negative skewness, the extreme values are smaller in the negative skewness. So you can see in this case, the extreme values are smaller, okay, and to the left. So which lowers the data set's mean value. You can see if it is smaller, it will reduce what, or it will lower, that is the data set's mean. Okay, for positive, we said it will increase. Okay, but for now negative, it will lower the mean value. Okay, so a negative skew distribution is one with the tail on the what, on the left side. Hence we are saying that mean is less than median and it's less than mode. Is that clear to everyone? Or maybe any question, or maybe any elaboration needed? Any question? Are we all together up to that point? Maybe by a show of thumbs up. Susan, okay, Deborah, Otieno, Steve, Collins, Frederick. Okay. I hope that is all clear. So in case maybe you are given a data set and you see maybe the tail is it's long to the what? To the right, okay? Then you can be able to know this maybe data is skewed to the right or is skewed to the left. Okay? All right. Good. Let's continue. Now let's go to kurtosis, or maybe the more elaboration about skewness. So in real life, data rarely or if ever follow a perfect normal distribution. So the skewness and kurtosis coefficients measure how different a given distribution is from a normal distribution. Okay, the skewness measures the symmetry of distribution. The normal distribution is a symmetric and has a skewness of 0. Remember that what we said for a perfect normal distribution or for a standard normal distribution, we say that the skewness is what? Is 0. Okay? So if the distribution of a data set has a skewness less than 0 or negative skewness, then the tail or the left tail of the distribution is longer than the right tail. Okay, and for a positive skewness implies that the right tail of a distribution is longer than what? Than the left. I had illustrated that. Okay, so and in skewness we've said that in statistics skewness is used to measure or as a measure of a symmetry of the probability distribution of a random variable about its mean. Okay, in other words, skewness tells you the amount of that is the amount, okay, and direction of skew. Okay, it shows you the amount and the direction of skew. Okay, that is departure from horizontal symmetry. The skewness value can be positive or negative. Okay, or even undefined. So we are saying that the skewness value can be a positive value or a negative value, okay, or even undefined. Okay, so if skewness is 0, then the data are perfectly symmetrical, although it is quite unlikely for real world data, that is as a general rule of thumb. Okay, if skewness is less than 1, then that is, if skewness is less than 1 or greater than 1, then we usually say that data is highly skewed, or our distribution is highly skewed, or basically our data is what is highly skewed. Okay, so if skewness is between -1 and -0.5, or between 0.5 and 1, we say the data is moderately skewed. Okay, and if the skewness is between 0.5 and 0. That is -0.5 and 0.5, then the distribution is what? Approximately symmetric, or it's approximately a normal distribution. All right. Okay, nice. Then we'll go now to that is to kurtosis. Okay, I would like maybe to do the kurtosis, and then after the kurtosis, now I can introduce that is the other distribution. Okay, that is binomial distribution. So we'll be done with normal distribution, then we'll move to binomial distribution. Okay, then go to central limit theorem, then do Poisson distribution, and then we'll do now the practicals for all those distributions. Okay, all right, that being said, I will lastly request maybe for 1 minute or 2 minutes. um, I'll be back, just 1 minute. Okay, thank you guys. All right. Sorry for that. I'm getting a lot of calls. Getting a lot of calls, so you'll pardon me. Okay, good. Now let's now continue with the kurtosis. Okay, let's continue now with the kurtosis. So for kurtosis, we have that is kurtosis. This is the formula. We also have a formula for skewness, and basically skewness is the third moment. Okay, that is from the mean, and kurtosis is the fourth moment from the what? From the mean. Okay. All right. Now let's try and see what kurtosis measures. Now, what kurtosis measures is the thickness and the thinness of the what? Of the tail. Okay. That is the thickness and the thinness of what? Of that is of the tail. Let's assume this is a perfect normal distribution. We have also another distribution which maybe might look like this. These are just illustrations. And then we have another distribution which looks like what? Like this. Don't worry about my curves, okay? Yes. So we are assuming this is the that is the norm that is the tails, okay? The thickness, that is thickness of the tail is this, okay? The shaded area. It's the thickness of what? Thickness of the tails. Okay. This is, we are assuming this is a perfect normal distribution or a standard, that is a standard normal distribution. Okay. Then we have another normal distribution with what? With thicker tails. Okay. This might be due to maybe change in what? Might be due to change. Is it change in standard deviation? Yes, this might be due to change in standard deviation, okay, of what? Of the normal distribution, while holding mean as what? As a constant. Holding mean as a constant, okay, mean as a constant, you will now have changes in what? In the tail. The thickness and the thickness. So you can see this one, we have thinner tails compared to the perfect normal distribution. So what kurtosis does, kurtosis tries to show us that is the thinness and the thickness of the tails, okay, from that of what? Of a standard normal distribution. Okay, for any distribution which has maybe thicker tails, okay, um, of course, we have its kurtosis value greater than what? Greater than 3. Remember, we said that for a perfect normal distribution, kurtosis is equal to what? Kurtosis is equal to 3. Okay? Meaning for any normal distribution with that is with thickness that is that where tails are thicker than that of normal distribution, okay, then we'll know that kurtosis is greater than what? Is greater than 3. Here, kurtosis will be greater than 3, and here, kurtosis will be what? Kurtosis will be less than 3. Okay? All right. So let's now check into the kurtosis. So the kurtosis statistics measures the thickness of the tail ends of a distribution in relation to tails of a normal distribution, or that is in relationship to tails of what? Of a perfect or of a standard normal distribution. Okay, so distribution with large kurtosis exhibit tail that or they exhibit tail data exceeding the tails of the what? Of the normal distribution. Like it might be or it might have that is 4 or 5 even more standard deviation from standard deviations from the mean. Like you can see, it is being affected by what? Standard deviation, assuming we are odding mean what? A constant. Okay. All right. Then the distribution with low kurtosis tail, that is data, exhibits that generally it has less extreme, or we have the data is generally less extreme, okay, than the tails of normal distribution. Okay, so the normal distribution has a kurtosis of 3, which indicates the distribution as neither fat or thin tail. Fat basically meaning thickness, okay, or it has neither fat or thin tails. Therefore, if an observed distribution has a kurtosis greater than 3, then the distribution is said to have heavy tails or thick tails or fat tails. Whenever maybe the distribution has a kurtosis that is value greater than 3, then the distribution is said to have what? Is said to have heavy tails. Okay, then when we compare to what? To a normal distribution. Okay, if the distribution has a kurtosis less than 3, then it is said to have thin tails compared to what? Compared to normal distribution. Okay, meaning basically here in this case we'll have less data values, okay, along the that is the tail, compared to what? Compared to standard normal distribution. And in this case we'll have we'll have more values within the tail, okay, in comparison to what? To a normal or to a standard or perfect normal distribution. Okay, I guess that is clear. Any question? Any question about kurtosis? Was that clear? Yes, Collins. Okay, so you were just showing a thumbs up. What about the others? Was that clear? Suzanne, that was clear. Collins, that was clear. Frederick, that was clear. Deborah, Gitage, that was clear. Okay. What about you, Steve? Was that clear? Yes, Otieno, that was clear. What about Steve? Okay. Oh, maybe he's not with us. All right. Let's now continue. So, as I had said, this is the formula. This is the formula for kurtosis. You can see it's the fourth moment. Okay. Yes. Then we are saying that, okay, we are saying that in this illustration that similarly many statistical theories attempt to model asset prices under the assumptions that they follow a normal distribution, but in reality price distributions tend to have fat tails, and therefore they usually have a kurtosis of that is which is greater than what? Greater than 3. Okay, so such assets have had price movements greater than what? Greater than 3 standard deviations beyond the mean more often than would be expected under assumptions of a perfect normal distribution. Okay? Even if an asset has went through a long period where it fits a normal distribution, we usually say that we don't have any guarantee, okay, that the past performance will tell us about what? The future prospects, okay? More so when we have maybe that is any that is kurtosis less or greater than what? Greater than 3, okay? Then with that we have that is central limit theorem. Okay, we have central limit theorem, and for central limit theorem, I will explain it in depth. Okay, I will explain it in depth. So under that is the central limit theorem. Okay, in probability, the central limit theorem, it states that a distribution of a sample variable approximates a normal distribution as the sample size becomes larger, assuming that all samples are identical in size and regardless of the population's actual distribution shape. Okay, so basically, like when we are dealing with what? When we are dealing maybe with a set of data, okay, we are saying that as we are increasing the sample size, okay, as we are increasing the sample size of our data set, okay, or of our sample data set, then that is the distribution. All that data set assumes a normal what? Assumes a normal distribution, okay, at a point. And also we'll see that central limit theorem also will tell us that also the mean, okay, as we increase the sample size, the mean and the standard deviation of our sample data will approximate the mean and the that is a standard deviation of what? Of the population, okay, because we are trying to move our sample data to approach what? That is a normal distribution. Sorry, the population that is the mean. Like for example, let's assume we have a population of 1,000, okay, and out of 1,000 we took a sample size of 100, okay. So as we are increasing these samples, that is sample size, okay, to 500, to 900, to 999, okay, you'll find that as we are increasing this sample size, the mean of this sample size, that is x bar, will approach the mean of what? Of the population, which is our mu. Same happens to the standard deviation, okay. So basically that's also what we are talking. Also, as we increase that is this sample size, we are saying that the data will now tend to assume what? Will tend to assume a normal distribution. That's what the central limit theorem that is depicts or states, okay. All right, let's try and see some takeaways under central limit theorem. So under central limit theorem, we are saying that it states that the distribution of a sample means approximates a normal distribution as the sample size gets larger, okay, regardless of the population distribution, okay. And we usually take that is for sample size to old, okay, n is always greater than that, okay. So for sample size equal or greater than 30 are often considered sufficient for central limit theorem to hold, okay. Yes, then a key aspect of central limit theorem is that the average of the sample data, or of the average of the sample means, okay, and the standard deviation will equal the population mean and what standard deviation at some point. That is, as we increase this sample size, okay, we will be approaching the mean and the standard deviation of what? Of the population. Okay. Yes. So we are also saying that a sufficiently large sample size can predict characteristics of a population more accurately. Of course, like as we increase the sample size, it's the more we learn or we get more insights about what? The more we get more insights about the population. Okay. Yes, it's like, for example, if we go maybe to do a research in maybe in a tribe, okay, and we want maybe to maybe we have a myth, okay, which is said to, maybe if you do this, this happens, okay. Then the village has a population of 1,000 people, okay. Then you decide to interview 10 people, 20 people. So definitely 10 people you'll get less insights, 20 people you'll get less insights. But if we do maybe like 900, okay, we'll get more information compared to when we interview only 100 people. Okay, so basically that's what the law of central limit tries to state. Okay, like we can say that for us to get a good characteristics of a population, we need now also to do what? To use a large sample size. Okay, and we are also saying that central limit theorem is useful in finance when analyzing a large collection of securities. CLT. That is, a central limit theorem is useful in finance when analyzing a large collection of securities to estimate portfolio distribution and trades for returns, risks, and maybe correlations. Okay. All right. Then we can say that central limit theorem is often used in conjunction with the law of large numbers, which states that the average of the sample means and standard deviation will come closer to equaling the population mean and standard deviation as long as the sample size grows, which is extremely useful in accurately predicting characteristics of the population. Yes, I guess this is what I had defined here above. Okay. Yes, so for that, I would beg